Mhm. Mhm. Okay, here is my screen, and let us comment. Should I do it? Okay. So we continue to discuss how to build the stochastic differential equation, which can describe the evolution of the system from the large number of interacting particles. These particles interact one with other and also with the random media. So this is the main question today. And today we will write the corresponding equation and see the properties of its solution. So let us start. Usually, the motion of one particle is described by the ordinary stochastic differential equation, like what is written. And here, the coefficient A is responsible for the external force, and coefficient B, together with Wiener process W, is responsible for the influence of the random media. Then let us ask how one can describe the motion of several particles. The idea is trivial, and maybe we can just write the system of stochastic differential equations. So we will see such a coefficients like for a fixed I, we have coefficients AI, which reflects dependence of the external force and the interaction with other particles. Also the same happened with coefficient B and dW I. So it is natural that for different particles we have different Wiener process. But the coefficients A are responsible not only for the influence of external force and the random media, but also for the interaction between particles. This is trivial in this formula, but important for us in the future. Also note that the Wiener processes, which are corresponding to any particles, must be dependent. And the explanation is very simple. Suppose that we have two particles placed in the random media. The random motion of the particles is caused by the interaction with the molecules of the media. And it is natural that due to the very large speed of the molecules of the media, we have at the fixed moment of the time, more or less fixed moment of the time, we have like clouds around the particle, and molecules from this cloud can interact and can have influence on the motion of the particle. But if particles are pretty close one to another, then we can see that these two clouds have a common set of molecules. And this is a reason why we have to suppose that Wiener processes describing the random perturbation of different particles must be dependent. So we, from this simple attempt, trivial attempt, to write the equation for the several particles in the random media, we get a few things. One is that the coefficients must depend from other particles, and another one that the noise related to every particle, the noises related to every particle must be dependent. Now look what happened when n capital became to be sufficiently large. What to do? It is trivial that we cannot write the special coefficient a where we will have like 100 variables or so. So we must choose special type of interaction between particles and use it. And one of the widest spread description of interaction between particles is the following. This is well-known sum of potential of two particle interaction. This here the sum is corresponding to the interaction of particle Ri with other particles of the system. The same can be written if we want to have a multiple interaction, for example, k plus 1. Then we use the following multiple sum, which reflects the interaction of the particle Ri with the sets of other particles Rj1, and so on, Rjk. In order to generalize or to extend this sum to the large number of the particles, let us introduce the distribution of mass of the particles. One can suppose that each particle have its own weight, Pj, and then one can introduce the measure. We yesterday have seen such measures. This is a discrete measure concentrated in the point where particles are located, and having the weights P in this point. Then one can write the multiple sum related to interaction between particles as an integral with respect to mu. So we just rewrite the coefficient which reflect multiple interaction between particles as a multiple integral with respect to introduced measure, mass distribution of the particles. So we can see that for large n, it is reasonable. It is reasonable to write system as follows. It looks like that we have differential for the fixed particle particle Ri, and it is equal to the multiple integral with respect to measure mu t. And this measure mu t is carried by the particles. Here is it. So we have the natural way in which the measure naturally came into the coefficient of our equation. More general, one can say that if we have a system of the particles with interaction, then its motion can be described by the differential equation like this, where the coefficient A now is corresponding to the influence of external force at the point Ri, and also is corresponding to the interaction between all particles. It's their influence on this particle Ri via its mass distribution mu t. And more general, and this is non-trivial step. Why? You see, yesterday we discussed the following question. What will happen if the empirical measure, empirical mass distribution, which will approach some continuous measure? Then for continuous measure, we have such interpretation that maybe we have to start from any point of the space. Because if mu is a continuous measure, then any fixed point has zero mass. But when they move as a measure mu t, and one can consider the following differential equation. We have dx ut equal to the a from x ut mu t. Here we start from any point of the space. U belong to Rd, and mu t is equal to the image of the measure mu0 under the mapping x ut. So this is a very important step from the equation for heavy particles. Now it is not important how large the number of these particles is. We make a step to the equation for all points in our space. Now we get a flow x. So this Cauchy problem, which you see on the slide, is the Cauchy problem simultaneously for measure-valued function mu t and for mapping x t. And this mapping, by the way, moves the initial mass distribution to the mass distribution mu t. So now let us, when we understood how to describe the interaction between particles, we understood that it can be described by including the measurable mass distribution argument into the coefficient of the equation. Let's go to the description of the interaction of the particles with random media. Of course, one can think how we will solve this equation, because it is new for us. It must be solved simultaneously for all u together. But of course, we expect that maybe we will need some Lipschitz condition with respect to both arguments, with respect to measure in Wasserstein distance. Yesterday, we discussed what is the Wasserstein distance on the space of probability distributions. By the way, this example is very important. If the function vk plus 1 from Rd in k plus 1 power to Rd is Lipschitz and bounded, then a u mu defined as a multiple integral with respect to measure mu is Lipschitz with respect u and mu, and with respect to mu in the Wasserstein distance of order 0. It is a good example which says us that we construct our equation in a right way. It includes now the multiple interaction between particles. Consider the example of deterministic equation with interaction of the following kind. It is a linear equation. It is maybe simplest differential equation which we study when we began to study differential equation. Here A is just matrix, and mu t is the image of initial measure mu0 under that mapping X. I suppose that initial mu mu0 belongs to M1, so it has the first moment, and it is not hard to check that mu t also will have the first moment, so we can integrate V against mu t. Here A is just fixed matrix, as I said. Now, to solve this equation, denoted by mt, the integral from Rd over Rd from V to mt, and this is like center of the mass of this measure mu t. This is an important characteristic of the probability distribution, and in the next lectures we will use it. So by change of variables formula, it can be written as such integral with respect to initial measure mu0. Then it is trivial by integrating the equation again with respect to mu t, one can get that differential of mt is equal to 0. Hence, mt is equal to m0 for any t, so the center of the mass of our system remains to be the same. And now we can finally get the formula for solution. Xut is equal ttu plus e minus tt m0, where tt is a semigroup related to the matrix A. It is a trivial equation, but one can have some conclusions from this equation. First of all, we say that m0 is mt is equal to m0. So center of the mass of our system is fixed. From this point of view, it is trivial that if we start from the measure mu0, which is concentrated in one point, then this measure remains to be the same during our evolution. From this point of view, we have interesting conclusion. You remember that in case of ordinary differential equation, if we consider linear equation, then it has attracting manifold, repelling manifold, and it can have some stationary points. And these stationary points are from 0 in the eigenfunction of matrix A. So, for example, if A is non-degenerated, the unique stationary point is 0. But now you see that for any matrix A, independently of the condition on matrix A, in the space of measures, this equation has a lot of stationary points. Any delta measure is stationary point for this equation. This is one. This is one remark. Another remark is let's again see the behavior of the solution xut. For example, suppose that matrix A is just minus positive definite matrix. Then it is trivial that xut goes to M0 when t goes to infinity. So all particles concentrate near center of the mass. In other case, if A is simply positive matrix, then all particles will run away from the center of the mass. From this remark, we can make the following conclusion. In the future, when we will study the limiting behavior of the solution to equation with interaction, we maybe don't have to expect that we will go to some fixed point in the space, to some attracting point, or in opposite case that we will have some fixed repelling manifold. Maybe we must study the asymptotic behavior relatively to the center of the mass, for example, of total mass distribution, of relatively to some other points or manifolds which we can build basing on the measure mu t. This is important remark. Now let us go to the interaction with the random media. And one can expect that we need to construct noises for every particles, but these noises must be dependent. So let us explode this picture which I drew. This picture which I drew as follows. Let us introduce the randomness, not only depending on the time as just one Wiener process, but also dependent on the space, and describe the clouds of molecules by some functions. And see what is the formal construction now. The interaction with the random media can be described with the help of integration with respect to Gaussian measure W on, you see here, the product RD space and time 0 plus infinity. And suppose that W has 0 mean and is such that here is tensor product because W is a vector measure. So I suppose that the expectation of such vector product is equal to Lebesgue of intersection delta 1, delta 2 multiplied by the identity matrix. It means that coordinates of W are independent, equidistributed, and W has independent value on disjoint sets. For particle which is placed at the point U at the time t, the instant influence of random media is described as follows. So we have the integral, you remember the cloud. I propose to describe this cloud by the function h, and of course this function must decrease to 0 when difference between position of the particle u and position of the molecular p goes to infinity. And we have such integral like it reflects the sum of influence of molecules of the media, and dt is corresponding that we trying to calculate this influence at the time t. So from technical reason, we suppose that H is from L2 RD. And now let's consider examples. It is interesting even to look for one particle which move in this random media. Let's suppose that this function h, our window of interaction with the molecules of the media, is such that integral from the square is equal to 1. Then for every u such process yut, which is equal to u plus integral from 0 to t integral of rd hu minus p v dp ds. So this process just describes random motion of our particle, one particle. This process is Brownian motion which starts at u. And it can be easily proved using Levy characterization of Brownian motion. It says us that if we have continuous martingale with characteristic equal to t, then this martingale is a Brownian motion. It is exactly the case because trivially this y is continuous, it is martingale, and due to our assumption that integral over rd of h square is equal to 1, the characteristic of y is identity matrix multiplied by t. So it is a Levy by Levy version or vector valued, so call it isotropic martingales. Y is Brownian motion. Now, see the following important remark. The processes y, u for different u are correlated. And it is also trivial because if we take yu1t and yu2t and just take expectation of the product, then we will get the integral from the product of the functions hu1 minus p and hu2 minus p, and this product is non-zero, at least for certain u1 and u2. So this Gaussian measure on the space and time give us possibility to construct a model of the interacting Brownian motions in the space. Okay, and now we are ready to write a general form of equation with interaction. Let us consider this general form. Dxut is equal axut mu t dt plus integral with respect to rd bxut mu t p w dp dt. And we start from every point of the space xu0 equal to u belong to rd, and mu t is an image of the initial mass distribution under the mapping xt. So mu t is a mass distribution of all particles at the time t. Here again, coefficients a reflect the influence of external force and interaction between particles due to the second measure valued argument mu t, and coefficient b also include interaction between particles and due to the presence of stochastic integral, it reflects the influence of the random media as we have seen before. So now let's think about the theorem which gives us the answer about the existence and uniqueness of the solution. Maybe everybody expects that if we have the Lipschitz condition, then we have a unique solution. It is true. Suppose that mu0 belongs to M capital M, and the coefficients A and B are Lipschitz, with respect to norm in Rd and gamma M in M in the space of measures with M's moment. Then the Cauchy problem for equation with interaction has solution, and this solution is unique. From the first look, the formulation of the theorem is natural, because we have a habit that if we have a Lipschitz coefficients of any equation, then we have a unique solution. But let me tell you some words about the proof of this theorem, because it has some specific features. The proof, of course, is based on the iteration method. So let us define this iteration. Let us write the equation for the n+1 iteration for x. And you see in this equation that I put the measure mu tn, and this process is obtained on the previous step. Then mu tn as usual is an image of mu0 under xn. And initially we start from the mapping x0, which is just identity map. This is a usual iteration scheme, but we have to solve some new problems. And maybe it is reasonable that when estimating the difference between the xn+1 and xn, we will use Lipschitz condition for coefficients, and we will get the distance between the measures mu tn and mu tn minus 1, for example. How to estimate this distance? Yesterday we have seen that Wasserstein distance is defined in complicated ways. As we remember, it is infimum over all set of measures which has mu tn and mu tn+1 as the marginal projections. So to estimate the distance between two probability measures, we have just take one representative from those set of set Q mu nu. And the problem always is only how to find the appropriate representative. Now it can be done as follows. Build kappa, which belongs Q mu t and mu tn+1 as follows. It will be a mapping of initial mu0 under such mapping. So we have two coordinates mapping. Every coordinate is RD, but we have two coordinates mapping. One is xn, another one is xn+1. Here, this is the mapping. It acts from RD to RD multiplied on RD. And then the distance between mu tn and mu tn+1 can be estimated through the distance between xn and xn+1. So we will have now the possibility to apply Granol-Bellman and and after this to use usual argument to get the convergence of the iterations. Also, another new technical moment is present here. And this technical moment is related to even to the definition of our iterations. Why? Because you see here mu tn equal mu0 under the image of x and t minus. To build such construction, to move our measure by the mapping xn t, we need some conditions on this map. We cannot move the measure mu0 by the arbitrary mapping. We have to check that it is at least measured. But of course, now under Lipschitz condition, using Kolmogorov condition, one can check that Xn has a continuous modification with respect to spatial variable. So
I'm sorry, may
yes,
I interrupt you? I have a question concerning the definition of kappa. So kappa, probably it is mu0 times mu0 composed with this.
No, Yana, this is the idea. This is the idea. You see, I said that this is a mapping. Please see this one. Here, xn plus 1, this is a pair, but
Yes.
it maps one variable. You see?
Okay.
This is the idea. Because unfortunately, I use such a program. Maybe next time I will use another program to demonstrate slide. Now I cannot write here. But the idea is that, for example, suppose that xn and xn plus 1 are identities. Yes?
Yes.
Then
yes.
You measure on the diagonal. If they are different, then we build measure on the some curve near diagonal, and how far this curve is from the diagonal. This is actually the estimation of the distance.
But kappa should have a dimension, so to say, twice more than mu0.
Exactly. And you see this pair of mappings x to rd multiplied to rd.
Okay. Okay,
Yeah?
so this is a kind of, I need time to understand it. Okay, thank you.
You're welcome. This is yes, this is a real trick, and and actually one of the main tricks during this proof of the existence of the solution. Because other tricks related to Grunwald, Bellman, to Burkholder, David Gatti, inequality to guarantee the convergence of semi-martingales are usual for ordinary stochastic differential equation, but this is new. Okay, then
Thank you.
is you're welcome. This is just new steps which we face when apply iteration method to prove the existence and uniqueness of the solution to equation with interaction. Now, let's consider the properties of the solution to equation with interaction. The first one is maybe expectable, but also very useful, that the mapping X and measure evaluate process mu t continuously depend on mu0. Actually, we expect this for ordinary stochastic differential equation under Lipschitz coefficients. Here we have the same statement, and of course, if we have a distance in the space of probability measures with m finite moment, then again we measure the distance between initial measures also in the same space. The next property is also technical but very useful. Suppose that our coefficients a and b are C2 with respect to spatial variable with bounded derivatives. Then X is a random diffeomorphism. Now let's go back. Go back to the formulation of equation with interaction. You see, here we have the equation simultaneously to mu t and the flow. But when we discussing the smoothness properties of the mapping X, we can proceed as follows. We already have the solution. Suppose that we input this mu t into coefficients and look at this equation only as equation for x and the known mu t. Mu t is already known. Then we will have a stochastic differential equation with the random coefficients, but with the smooth coefficients. And it is a well-known result from, for example, from a book of Kunita, that such equation with a random smooth coefficient, spatial smooth coefficient, have a diffeomorphic solution. So this is a way how to check this. So we have this technical property, but it is very important, and we will see how it works in the future. Also, we say that we have unique solution. As usual for stochastic differential equation, when we have a unique solution, we can expect Markov property of the solution. Because if we stop somewhere, we can start for future time, forgetting about what happened before. Yeah. So the Markov property, even strong Markov property, can be proved in a usual way, but for what? For which process? For arbitrary m and fixed starting points u1 and so on un, the process mu t and then xu1t, xun-t is Markov process. As we said, it even has strong Markov. In particular, measure-valued process mu t itself is Markov process in the space of measures. By the way, now we make non-trivial steps because we construct some class of measure-valued Markov processes of constant mass. It is not a subject of consideration of our lectures, but I have to say that there are different constructions of measure-valued processes of constant mass related to different mathematical models. Maybe one of the well-known model is the Fleming-Villot processes related to population genetics. But in our case, we construct the class of Markov measure-valued processes related to the motion on the initial phase space. Even more, we have seen that during this motion, due to the property 2, that X is a random diffeomorphism, particles cannot jump, cannot split on two particles or turn into clouds. They have to move like a solid particles. Yeah? Also, it is interesting to see that in general, if we fix xut, just one point, and start to watch the motion of this one point, it is not Markov process in general. So it is interesting to associate this with passive traces in the liquid. Suppose that you have a turbulent liquid flow, and you put in this flow one particle. Of course, it looks that and it is true, that the motion of this one particle is Markov process. Yeah? But if you put sufficiently large amount of traces in this liquid, they begin to interact one with another. and the knowledge of the position of one particle at fixed time t is not sufficient to predict its future, because it can collide with other particles. So this is a rough explanation of the reason why in general XUT is not Markov process. We have a slightly complicated object with new features, and it looks like that we must have to build new intuition about this object. But let me give you an interesting example how one can build equation with interaction with the usual ordinary stochastic differential equation. So let us use the random time change procedure and how it looks like. Let us, I will consider one dimension. Let us consider the stochastic differential equation with good coefficients. It is smooth enough, they are smooth enough, and so on, with one-dimensional inner quotes W. Now this stochastic differential equation generates a flow on the space. So let us suppose that denote this flow by G capital 0s. This is the solution which starts from U at the time 0. Now fix some probability distribution mu 0 on R, and function phi on which belong to C0R. I forgot to write here that phi must be positive. It must be positive. Then define the following measure nu t. It is a measure which is constructed the way familiar to us. So we have the flow related to ordinary stochastic differential. It is a good flow in a modern language. It is called a random dynamical system. Yeah, we have a good stochastic flow, and we just move mass distribution, initial mass distribution over the space. There are no any interaction. We just move this mass distribution. But now let us construct so-called additive functional from this flow. And this additive functional looks like that. I or I capital of t is equal to integral from 0 to t, integral with respect to r with this phi d nu s and ds. So what happened? We just consider the amount of weights collected by our function phi during a time from 0 to t. And this is additive functional. Moreover, it is non-decreasing, yeah, because as I said, phi must be non-negative. And then one can take the inverse function, a general inverse as usual. But I will suppose that nu is probability measure with the support equal to r, in order to conclude that I is strictly increasing function. It is just technical condition, but we needed to say that the inverse function is exactly inverse function in the cell of analysis first course. Then one can change the time. You see? So what I do, I consider the initial trajectory of our ordinary stochastic differential equation But now I am looking for these weights which are collected by the function phi. If we collect a lot of weights, then tau became to be smaller than t. So we just we push brakes. And if in opposite case, tau is can be greater. Yeah? And it can, this is just martingale technique. It can be checked that XUT satisfy new equation with the coefficients which depend on what? On the position of cos XUT, on the integral from mu t with the function phi. And what is mu t? Mu t is an image of initial mass distribution mu zero. So we produce the equation with interaction for time-changing trajectories of the initial ordinary differential equation. So the picture is like following. We have the ordinary differential equation. We have stochastic flow with no interaction. And we introduce interaction just looking for the weights which are collected by some function, fixed function phi. And we just make time change. If we collect a lot of weight, we move slowly. If we collect more weights, we less weights than in other points, we move faster. So this is the idea, how one can get the equation with interaction from the usual stochastic differential equation. Of course, it must be noted that we will have a very special coefficients, They are not of the kind which we discussed with you in the beginning of the lectures. Let me recall you which coefficients we discussed, like this one. They are not of such kind. So from the point of view mathematical modeling of the real processes, they are not, they are artificial. This what I wanted to say to you in this lecture, but let me say what we will have, what we will do further. You see these coefficients, and you see this example. After this look, it is natural to say that maybe asymptotic behavior of the equation with interaction will be very different from the asymptotic behavior of the solutions to ordinary stochastic differential equation. And why we are looking for the asymptotic behavior of the solution to any stochastic differential equation? Because, as I said in the last lecture, we are looking for some stationary behavior of the system. So we need to in conditions for existence of the stationary solution to our equation. But you see this one, we have a lot of stationary points, and you see that our solution is moving around the mass, center of the mass. So from this point of view, it looks like we will have some troubles when we will discuss the existence and properties of stationary solutions to equations with interaction. So our next plan, our future plans is following. Tomorrow we will discuss the widespread tools and conditions for ordinary stochastic differential equations, which guarantee the existence of the stationary solution. And we will think how we can apply this condition to the case of the equation with interaction in the next lectures. And we will see some surprises. But this is in the future. For today, this is all what I wanted to say. Thank you for attention. And maybe somebody have questions or comments, please.
Would you please show the last equation with interaction, which was in the example?
Here is it.
Okay, thank you.
Mm-hmm. And as I said, it is unnatural. It is artificial, of course. It is just to show you how the interaction can occur. Yeah.
Mm-hmm.
Mm-hmm. Okay. You're welcome.
So the last sentence is particle move along all trajectories, but with different speed. Okay, thank you.
Yeah. We just change the speed.
Mm-hmm.
Okay. Okay. If there are no other questions, then thank you for attention, and see you tomorrow. Bye.
Thank you.
Bye.
See you tomorrow. Bye. So tomorrow the same time. Let's meet.